Hello, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today, we have Alan McNeil. Alan is the product line manager of ferrite and waveguides. Also joining us today is Tony Booth. Tony is a senior principal engineer. So to read more about our presenters today, go ahead and look at that speaker bio window right next to the main presentation window. Now I would like to go over today's goals. So we're going to review the evolution and utility of MFAs in mission-critical applications. We're going to understand the trade-offs in deciding whether to opt for an integrated versus a discrete assembly. We're going to discover the benefits of MFAs and decide for yourself if these benefits work for your application. And then we will have a brief Q&A session. So with that, I'm going to pass things over to Alan to get us started. So Alan, go right ahead.
Thanks, Katie. So this slide is meant to convey what we mean by a multifunction assembly. So there's a little illustration here, and the illustration at the top is three components chained together. Could be RF connectors, it could be waveguide. And these components tend to be purchased from separate suppliers, specified differently, and then put together in the chain. What we mean by an MFA is illustrated in the bottom diagram, where you can buy all three components from a single supplier, perhaps us, and by integrating them together, we can get some benefits, more than the benefits of the individual components. So generally, MFAs offer direct benefits over a chain of components in three main ways. Superior electrical performance, it's a more compact and lower mass solution generally. And an interesting one is mechanically much more robust, meeting better dimensional tolerances, which is often an issue in high-frequency components. There are also some indirect benefits. They are simpler to specify and purchase. So instead of, in this case, specifying three components, you'd be specifying one. They're simpler to integrate because there's less issues in terms of tolerancing, etc. And they're more reliable. So we're going to show you some examples of this, but first, Tony is going to talk you through these in greater detail.
Thanks, Alan. So here are some of the main advantages an MFA gives. So firstly, electrical benefits. Say at X-band, around about 9 gigs, the loss of a connector is approximately 0.1 dB. So this is often a major contribution to the loss budget. By integrating, we can significantly minimize this by simply reducing the number of connectors. We can also manage and optimize the component interactions. Say two worst case VSWRs multiply together. So if you have 21 dB return loss, this can result in an overall return loss of only 15 dB. So we can take care of this headache. An MFA also has obvious EMC benefits, less connectors, reduced number of housings, lids, gaskets, etc. Okay, so mechanical benefits include improved vibration, thermal robustness, alongside the reduced volume and size, which is always key for applications. So Alan, anything else to add?
I guess there are the intangible benefits, which we've alluded to, but to be honest, only the customer can decide how important or how valuable these are. And I guess the other thing to add is that the cost, the development costs, they're finite, but they do depend on the complexity and the starting points. So if we've got good starting points in terms of components, and we put them together, the costs will certainly be lower. And certainly the more complicated the MFA, the greater the benefits become. So this is an example of a UHF filter assembly. The schematic is on the screen in front of you. And it's used in a proximity receiver, for a deep space emergency communication system. So basically, this is a safety of life component, so it must be absolutely reliable. Astronauts will be using this sort of component in the future as part of their backup communication systems if all else fails. So basically, this component has got to work flawlessly.
Okay, thanks, Alan. So the transmit filter, which is this filter here, so this is a 5-section cavity filter with one triplet cross-coupling. So it's a capacitive cross-coupling, so it gives a sharp, deep rejection on the low side. You'll note the dielectric here. So this is to suppress any multipaction which you could see at this very, very low frequency. On the receive filter, so a receive filter is a 6-section Chebyshev with no cross couplings, and you'll note there's some supports on the ends of the resonators to stop these vibrating. And then the final image here is the whole assembly, which has been looked at through vibration modal analysis. So we can manage the full resonant frequency sweep, so we can check the whole MFA is resonant free beyond 2000 hertz.
So this is another application for a space system here, and this time it's on a satellite that's broadcasting CD quality radio. And this is an example where we got into this and we realized that the customer hadn't been fully aware of their own requirements, but we continued on with them. And they gave us a form factor, which is the form factor shown there, and it turned out that they needed very, very tight group delay matching. Now, group delay matching is pretty expensive to achieve with a system that contains isolators. These isolators, which are the images which are shown here. So this is an isolator. These are all microstrip isolators. And these isolators tend to have a transmission frequency of the order of several thousand degrees. So making them group delay match is actually quite challenging. But by using this arrangement, by integrating the arrangement with this device, we not only managed to meet the requirements, but exceed the requirements. And had we been using a standard strip line isolator with this 1-to-6 splitter, we would not have met that specification. Now, these microstrip isolators, normally you bond to them. So in the area that I've highlighted here, there are wire bonds. In this case, the customer obviously wants an SMA box. So what we did here is we actually developed a process to give us a sliding fit connector from the connector here onto the microstrip device. So not only was it now working group delay matched, it was inherently incredibly robust. So our customer came to us basically because we had the capability of developing this kind of processes and packaging capabilities. But what the lesson that I learned here was be fully transparent before you go into this. Understand what the customer's expectations are. So this is another example where the customer was absolutely sure what they wanted, and it was an incredibly low cost. So this is used on a low cost coastal surveillance radar. It's a high power duplexer. So the image you have here is you've got 1, 2, 3 ports. 2 of them are in coax, here and here, and this is in waveguide. And there are a number of these devices in this antenna system. The schematic is shown here. And what drove us in this direction was cost more than anything. The electrical performance kind of comes out the wash, but the component interactions were important, but the cost was everything. So we have here an example where we were taking these items here, which are all brazed assemblies. So brazed assemblies are generally low cost if you make enough of them, but we had to integrate them with this precision machined isolator. So it didn't make sense to actually braze the entire assembly together. To give you an example how big it is, from about here to here, it's about 36 inches. So it's quite a large device. Tony, do you want to expand on the electricals here?
Sure, yeah. So the image here is a waveguide waffle iron filter to reject up to 6 harmonic. So it's double cascaded. So there's actually 2 waffle irons cascaded together. So that means we can take care of any return loss interactions, but also any potential phasing spikes in the stop band as well. And the graph here is there's lots of transmission lines here. So this is actually looking at all the potential propagating modes. So both the TE and TM modes. So we analyse with all modes just to ensure that when we actually test the device, it will give full compliant rejection up to 6 harmonic.
So this is another example of a space product. It's going to be used in a TT&C, telemetry, telecommand and communication system. And it's an example where we can really start to add value. So key things for our customer here were mechanical size and cost, and it needed to be super robust for obvious reasons. So the important considerations are cost in this case and mechanical size. Tony?
Okay, so the input to this is actually on the right. So the input is first a 3-section small cavity filter with a simple triplet cross coupling. So this gives us a very sharp transmission zero on the high side. The next is a tubular low pass. So this rejects harmonics up to 8th harmonic, so we're rejecting up to about 32 gigs. Followed by a printed directional coupler, and finally the coaxial isolator. So a few things to note on here. So all interconnections are used in sliding contacts to give stress relief and minimise insertion loss. So the input return loss on the measured prototype of this was actually greater than 20 dB, which, to be honest, was a great result considering there's 4 RF components cascaded together. Also, something to note is the isolator has some rather special harmonic characteristics, so we can actually exploit that. So when we cascade with the low-pass filter, we can actually make the low-pass filter slightly easier. So we can take out a couple of sections, and that will lower the insertion loss and size.
So this is an example where the driving requirement was not as much electrical as mechanical. So what we have here is an 8-to-1 power combiner. So you can see each of the inputs here. There's 8 of them, and these are orthogonal transitions. And there's 20 watts going into each transition through an SMA cable. And these are driven from the customer's SSPAs. And in fact, the SSPAs are actually mounted on the reverse side of this structure. And the structure is actually used to provide not only mechanical rigidity to the system, but also to act as a heatsink. It's a fair lump of metal. So we have the eight channels being combined through a series of 3 dB hybrids. The loads are all internal. And on the output, we have a high power isolator. Now, it's a 160 watt isolator. The insertion loss is only 0.1 of a dB. And the reason it's not integrated into the structure is this structure is actually done in half height WR112. The isolator is done in full height WR112, so it didn't make sense to integrate it. So it's an excellent example of where understanding where the customer sees value. In this case, obviously, there's electrical specification, but they saw value in the mechanical structure. This device is used in a tracked vehicle uplinked to a satellite, and there's not a lot of space, so making it nice and compact not only drove advantages for the customer system, but it also drove advantages for the electrical performance, because every time, as Tony said on the previous slide, every time you add an interconnect, you add a fraction of a dB. So there's a 1, 2, 3 cascades of device here, and each of these would, the integration removes one flange interface. So probably taking about 0.1, 0.15 dBs out of the insertion loss. So this is if this looks familiar, it's because it's actually an identical functional block diagram to the C-band one that Tony was describing a couple of slides back. In this case, it's the same customer, and the customer liked this idea so much they decided to adopt it for KU band. The problem was, of course, that they needed this to be super compact, And although KU band, you'd expect it to be a much more compact structure, the challenges meeting the insertion loss meant that we had to do some pretty clever things. So, Tony, can you talk us through the features there?
Sure. So again, the input is on the right. So to meet the very tight insertion loss and rejection spec, we had to use a more higher Q structure. Hence why we used waveguides. So what we first did is we transformed from coax into waveguide with a ridge transformer. Then there was a low pass section, so a simple waffle iron to reject harmonics up to 32 gigs. And then the bandpass section is this section here. So this is a corrugated style filter with multiple transmission zeros on the high side. So that's what you'll see with these slots in the waveguide. So these give very tight rejection. So you're talking about a 250 meg guard band here, so up to 50 dB. So it's very tight rejection. And then we transform out of waveguide back into coax, and then we have the coupler and the isolator as well. So again, all interconnections are using sliding contacts where appropriate. And the simulated input return on this is 20 dB. So the real test date is going to arrive in a couple of days' time. So this is a real good example of we're cascading 7 RF components here. So yeah, we take into account all the interactions and just optimize to get the best possible performance. Again, the special harmonic characteristics of the isolator has been exploited to use that in conjunction with the low pass section as well to ensure we have full rejection up to 32 gigs.
So this is an example, another example in waveguide. It's used on a low power radar assembly. When I say low power, it's 60 watts. So not exactly low power, but it works on the ground. And it's an example where you have 2 identical halves illustrated in the schematic here, and they're phase matched. Now this is an interesting one because in this case, the customer actually gave us the envelope and said, has to be this size. These are the interface points, no deviating. And by the way, we have to actually mount our circuitry and all our bits and bobs onto your structure. So we started off with some pretty tight mechanical constraints. And the key thing for us were actually trying to get it to fit it into the space. We used a combination of half height and full height waveguide pieces. But what we decided to do, instead of integrate the filters, is to put the filters separately. And that's because the way it's machined, we have to machine this in 2 halves, but the filters are actually at right angles to the machining faces. So it kind of made sense to put the filters as standalone. Plus, we get the chance to change the filters in future if the legal requirements which dictate the filter characteristics actually change. So an MFA was selected primarily because they needed insertion loss and they needed low cost. This is going to be made in pretty reasonable volumes. We're in serial production at the moment. And it was probably an example of where everything played to an MFA's strengths. So mechanically more robust, electrical performance, mass and mechanical tolerance. And I guess the other thing which we brought to the party was not only the mechanical design skills, electrical design skills, was our ability to high power test this, or power test this as the case may be, and our qualification laboratory. So we'll be able to take the structure and subject it to vibration and mechanical shock testing. So all in all, it was an excellent outcome. Tony, can you talk us through the salient features, please?
Yes, sure. So as Alan alluded to, they are closely phase matched. So the left-hand side and the right-hand side are identical. So the actual waveguide filters here and here. So they are 7-section waveguide Chebyshev filters. So but what's called a metal insert or septum type filter, so that they're split down the E-plane and then screwed together with a fin septum. We have inside here we have multiple E and H plane bends, which helps for compactness. And again, we can take into account all the interactions between the bends, the filters, the junction, etc., to give a very, very good return loss and low insertion loss structure. There's high directivity cross-guide couplers integrated as well. And as Alan mentioned, here's the machined areas for the customer to fit their own circuitry in as well.
So this, there are 7 components in this assembly. They're bolted together, as you can see. And frankly, the customer could have easily purchased these 7 components and done the assembly themselves. However, in this case, budgets were under pressure, and integrating these meant that instead of supplying 7 sets of test results, we reduced this to a relatively straightforward 4-port system. So what drove this was cost savings. So here we have each of the ports. You can see the ports here. It's an SMA system, even though, well, SMA 2.92, I should say, and even though it's an SMA coaxial system, the entire assembly is actually done in waveguide. So we have the transitions into the hybrid, and we have the isolators and the transitions out of the system. Now, you normally get about 20, 23 dBs of isolation in a hybrid, but in this case, the customer wanted in excess of 46 dBs, so we had to use these isolators. So as an example where electrical performance was important, but what drove this was the customer's desire to get a very low cost. And in case anybody's wondering, this system is still orbiting Mars. It's part of the communication systems that relays data back to Earth. So this system is very high power, 63 watts, and this is not a typo. It's not WR112. You can see by the size of the waveguide is WR12, and it's operating in the band approximately 81 to 86 gigahertz. And this is an assembly which has been designed for 2 reasons. It's been designed to be made in very high quantity, incredibly low cost. And to reach that cost, we have to actually assemble it using pick and place. So it's an E-band system that will be assembled using a cobot. So it's a planar structure. It's been designed to be made cheaply. And inside this system, we've integrated, there are 2 hybrid couplers, there are 2 phase shifters, and there are 5 different RF loads. So one load in the forward direction is designed to give approximately 12 watts of power handling, and then the other way it takes the full 63 watts should there be a fault downstream the system. So what attracted our customer to us in this case was a number of things. First of all, we thought we could do it, and we had the test equipment to do that because it's not every company has 70 to 110 gigahertz VNAs. We also had the experience of making this type of product using automated assembly, and we could do all the good things of the RF and thermal modeling beforehand to prove this would be the case. But fundamentally, what really got them interested was the price that we had on the table. Unfortunately, I can't share that with you, but you would think as you go towards E-band, things would get more expensive. In the quantity that they need these in, it's going to be incredibly low cost. This is going to be used in a ground-based satellite terminal, so ground to low Earth orbit, constellation communications. So this is another example of new space, and again, same drivers, high volume, but this time we're in the orbital portion, and our customer is looking for something incredibly compact. And here we have an example of that. So mass is everything, and you can see here this is the representation of this component here. But ultimately, we're going to move to this, and the reason our customer is working with us is the same reason as before. It's mass. Now, this particular device weighs just a little over 1 gram. It's going to be very cost effective because we're going to make it using robotic assembly. It's going to be process controlled, and we don't think we're going to need to test it. But this is tomorrow, but this is an example to show you what direction we're moving in. Tony? Okay,
thanks, Alan. So as you can see on the desired state here, there's two filters here. So what we're looking at doing here is printed thin film filters. So we can create diplexers using this technology to either split or combine signals, even if the bands are very, very close together, because we can use the hybrid. Of course, interconnects are all taken care of, including any RF or any thermal mismatch effects.
So this is the last example we're going to share with you, and this is an example to drive home the fact that when it works, when it goes right, it goes very, very well. This device, you can see with the lid off, is a commercial marine radar duplexer. So if you were to go to any port, see any pleasure boats in the port, probably a number of them would have this system within the radar. You can see the schematic here. So it comes in with a circulator, goes through a low-pass filter, and out through a circulator. And what drove our customer towards us wasn't the fact that we could do this, because it was fairly straightforward, but the fact that we had the integration expertise. In this case, we actually opted to use an investment casting. So quite an expensive thing to do, an investment casting, but they planned for this product to go into pretty high volume. And what I can share with you, since in the last 28 years, we've supplied a little over 550,000 of these waveguide assemblies. So the TWT comes in here. There's an isolator. There's a low-pass filter. And this is the output here. The output goes out through this transformer. And we have the option of putting a diode limiter in here if we want. And this is the receive port. So quite an exciting product back then, but just when it goes right, it goes very right. And I think 500,000 devices later, I think we can't say that we've had a more successful device than this.
Thanks, Alan. So,
oh, sorry, I beg your pardon.
Yeah. Okay, so the low-pass filter here again is a waveguide waffle-iron filter to eliminate harmonics. So you'll notice how close they are to the ferrite transformers. So we squeezed the size down to reduce the mass and cost as much as possible. But this still provides a very, very well matched solution. So again, we've took into account all the interactions between our components to give a very, very good final result.
So the previous slides have hopefully demonstrated the key skills required to successfully deliver an MFA solution. I hope they've provided some ideas for you of what we can do, and generally, specifically, what we might be able to do for you. So if I can summarize the basic themes, I think it's obvious that electrical design skills are clearly required, but these are no less important than the mechanical skills that are required to package them together. And to be honest, mechanical skills and electrical design skills would be nothing without the operational capability to produce them and the supply chains to support that, and the capability to test them, and if needs be, to qualify them for an intended application. I think technical success, however, is as important to commercial success. And the other lessons that we've learned in our journey producing MFAs is understanding your customers' motivations, expectations, and importantly, their business case. Because these three things are critical to making the right design approach decisions. It's got to be right for your customer, and it's got to be right for you. I think mutual understanding of these expectations, etc., and a willingness to be transparent over the design costs and the risk and risk mitigation strategies is what makes a good solution into a mutually beneficial, great solution. So Smiths has invested in this business to provide us the skills and the tools necessary to deliver MFA solutions for any market whether it's for defense, space, industrial, or avionics. And there's an example of each in the slides that you've just seen. We couldn't deliver the solutions that we've described without having a comprehensive capability, both in terms of design, manufacture, and test. So I think it's important that this is actually realized, because when selecting your vendor, you really need to make sure they have the whole list of package in front of them that they can bring to bear on you. So I think that's the last slide. Thanks for attending. Thanks for those that helped us prepare this and kept us on track. And thanks, of course, to my co-host, Tony, for lending his technical weight. I think we have a little time. I think we've got a little time for some questions, if there are any questions. Katie?
All right. Thank you guys both so much. So Alan is correct. We're going to move into a Q&A session at this time. All right. So Alan and Tony, let's move into our first question here. Alan, I think, or Tony, actually, I think this one could be for you. All right. This person is asking, can an MFA help to minimize the unwanted effects of multi-paction in a high power space environment?
Okay, thanks, Katie. So the short answer is yes, certainly it can. So there'll be a reduced number of coaxial connectors, which naturally will reduce the probability of any potential multi-paction events. Any interconnects will be certainly managed by us. So with these sliding contacts, which was a theme throughout the presentation, we can use special techniques to prevent multi-paction. Another thing as well is, being as we are minimising any VSWR mismatches, then I think that will certainly improve the multi-paction threshold as well. Instead of having, say, 3 or 4 different components where the VSWRs are being cascaded together, so you're getting higher and higher voltage multiplications, that certainly will help. And probably finally, testing will be certainly quicker and more cost-effective, because of course, we're only testing one component, the MFA, whereas if it was a collection of separate components, then every component would need to be multi-paction tested, and this, as people know, is very, very labour-intensive and very, very costly. So yes, certainly the answer is yes. It certainly will help minimise multi-paction.
Right. Thank you so much for that answer. All right. So, Alan, I think we can go over to you for this one. How long does it take to develop the types of things we have seen here?
Excellent question. It kind of depends on your starting point. If you have a lot of components in a chain which already exist and your job is to package them together, then you should be able to do it kind of quickly. But it also depends on your customer, because as I've sort of alluded to in several of the slides, customers not always 100% sure of what they need at the outset. But if I can talk typically, in the case of the example where we developed the UHF part, it was probably about a couple of months of development time. Then we're waiting another couple of months or 3 months for materials. So say 6 months, which is not uncommon in a space environment. If you take the example of the device, let me just call it up here. If you take this device, this initial part of the MFA was probably developed in about 14 to 18 weeks. So yeah, I think anything from about 5 to 6 months would be fairly typical.
All right. Thank you so much for that answer. Okay. Moving on to the next one here, gentlemen. This person is asking, we don't need an MFA, but some of the capabilities are interesting. Are you willing to supply just the component?
Well, the answer is absolutely yes. I mean, we started off as a components company. we are a components company who actually makes multifunction assemblies as well. So the answer is an unequivocal yes. Just send your requirements in and we'll deal with them.
All right. Thank you so much, Alan, for that answer. So just a note for the attendees, don't forget to grab those items out of the resource widget while we're answering a couple questions here. And if you don't hear your question being answered, don't worry. We'll reach out to you following today's webinar. All right, gentlemen, we have a couple more in our queue here. This person is asking, was there a weight limitation on this assembly?
Which assembly was that, Katie?
So if that attendee could maybe specify the exact assembly they were speaking of, that would be great. That way we can get that question answered. So we'll just give them a second if they want to type back in, or we can reach out to them following the webinar. So let's move to the next one here and see if we get a response on the other. So this one is asking, do you ever work directly with cable assembly companies when designs have coax cable runs, or is that entirely handled by the customer?
Tony, I'll handle that. If you take, hang on, let me just push this one. If you take this as an example, then you can see here we've got the UHF diplexer, we've got the circulator here, and we've also got some cables in here. So occasionally we do it, but I would say in most cases our customers tend to have their own preferred cable manufacturers. They know what their cable runs are. So I would say it's unusual, but we have done it and we can do it.
All right. Thank you so much for that answer. All right. So we are going to start to wrap the webinar up right now. If that attendee wants to specify the assembly for us, we can get back to you following today's webinar. And anyone else that has a question in our queue today, we will reach out to you following today's webinar. We are getting close to the end for today. If anyone else has a question or comment, you can also enter it during our on-demand period. So feel free to come back and enter any questions or comments you have at that time. And then before we end things today, just remember to grab those resources out of the resource widget. All right, so Alan and Tony, I want to say a huge thank you to both of you for being here with us today and for a great presentation and answering a few of our attendees' questions. So gentlemen, thank you both.
Thanks, Katie.
Thank you.
Bye-bye. Bye.
All right, and just a couple of closing remarks as we end things today. Again, thank you all for taking time to attend today's webinar event. Take care, and we will speak with all of you soon.